What if everything you think you know about reality is just a tiny fragment of something infinitely larger? Picture this: somewhere out there, beyond the edges of our observable universe, another version of you might be living a life shaped by choices you never made. It sounds like the plot of a sci-fi blockbuster, but this is the startling premise of eternal inflation and the multiverse theory, one of the most provocative ideas in modern cosmology. For centuries, we've believed our universe was unique, a singular cosmic masterpiece. But what if it's just one bubble in an endless froth of universes, each with its own laws of physics, its own history, its own version of you? The implications are staggering, and today we're going to explore 32 controversial models that push the boundaries of science, philosophy, and even imagination. Think about the last decision you made: what to eat for breakfast, whether to take that job offer, or which path to walk down. Now imagine that every possible outcome of that choice spawns a new universe, a new timeline where a different version of you exists. This isn't just wild speculation, it's a serious scientific proposition rooted in quantum mechanics and cosmic inflation. Some theories suggest that our universe is just one of countless others, bubbling into existence like foam in an infinite ocean. Others propose that these parallel realities are stacked like pages in a book, separated by dimensions we can't perceive. And then there are the models that challenge even these ideas, suggesting realities so strange they defy human intuition. Why does this matter? Because if even one of these theories is true, it means everything we've ever known, our place in the cosmos, the nature of time, even the concept of existence itself, could be radically different than we've ever imagined. This journey isn't just for physicists or philosophers. It's for anyone who's ever looked up at the night sky and wondered what's really out there. Over the next few minutes, we'll unravel the mysteries of bubble universes, quantum fluctuations, and dimensions beyond our perception. We'll examine theories that range from the rigorously mathematical to the wildly speculative, each offering a unique lens on reality. Some will leave you awestruck, others might make your head spin. But one thing's certain: by the time we're done, you'll never see the universe or yourself the same way again. So let's dive in, because the secrets of existence are waiting, and they're stranger than anything you've ever dreamed. To understand how our universe could be just one bubble in an infinite cosmic sea, we need to rewind to the very beginning, or at least what we think was the beginning. The concept of eternal inflation builds on the idea of cosmic inflation, that brief but unimaginably rapid expansion of space-time right after the Big Bang. But here's where things get wild. Imagine inflation doesn't stop everywhere at once. Instead, picture space as a bubbling cauldron, where some regions keep expanding exponentially while others slow down and settle into stable universes like ours. Each of these slowing regions becomes its own self-contained bubble universe, with its own unique physics, its own version of reality. What keeps this process going? It all comes down to quantum fluctuations, tiny, random ripples in the fabric of space-time. In regions where inflation continues, these fluctuations can create new pockets of space that start inflating all over again, birthing new universes in an endless cycle. Think of it like a chain reaction, where each spark sets off another explosion forever. And here's the mind-bending part: because this process never truly ends, the number of universes isn't just enormous, it's literally infinite. Now, you might be wondering, if we're trapped inside our own bubble universe, how could we ever prove others exist? That's where the controversy begins. Some scientists suggest that if another bubble universe collided with ours, it might leave a faint imprint in the cosmic microwave background, the afterglow of the Big Bang. Others argue that the very nature of these bubbles makes them forever hidden from us, like ships passing in an unimaginably vast ocean. But whether we can detect them or not, the math behind eternal inflation is surprisingly robust, rooted in the same equations that describe how particles behave at the quantum level and how gravity warps the cosmos. This isn't just theoretical gymnastics. If eternal inflation is real, it could explain some of the biggest mysteries in physics, like why the constants of nature seem so finely tuned for life. In an infinite multiverse, every possible combination of physical laws exists somewhere, and we just happen to live in the one where conditions are right for stars, planets, and us. It's a humbling thought that our entire reality might be a cosmic accident, one possibility among countless others, but it's also exhilarating because it means the universe is far stranger and more wondrous than we ever dared to dream. At the quantum level, reality behaves in ways that defy common sense. Particles pop in and out of existence. Energy fluctuates unpredictably, and empty space isn't truly empty at all. These tiny, fleeting disturbances, known as quantum fluctuations, might seem insignificant, but in the context of eternal inflation, they become cosmic architects capable of birthing entire universes. Picture a roiling ocean where random waves occasionally grow so large they break off, forming entirely new bodies of water. Similarly, in the seething fabric of space-time during inflation, a quantum fluctuation could trigger a runaway expansion, pinching off a self-contained pocket universe with its own unique physics. What makes this idea so compelling and controversial is that it suggests our universe might not be special at all. Instead of being meticulously designed, it could simply be the result of a random quantum jump, one possibility in an endless sea of alternatives. Some of these pocket universes might have stronger gravity, making stars burn out in seconds. Others could have no electromagnetism, leaving matter formless and dark. The unsettling implication, the laws of physics we consider fundamental, might just be a local ordinance, relevant only within our cosmic neighborhood. Critics push back, arguing that without a clear mathematical framework to show how these fluctuations stabilize into full-fledged universes, the theory remains more philosophy than physics. They point out that while quantum mechanics allows for randomness on a subatomic scale, scaling that up to create an entire universe is an enormous leap. Yet supporters counter that the same quantum principles governing particles also shape the large-scale structure of our cosmos, so why couldn't they spawn new ones? The debate hinges on a deeper question: is the multiverse a natural extension of known physics, or a speculative step into the unknown? This model forces us to confront the limits of causality itself. In a traditional universe, events have clear causes and effects. But if a quantum fluctuation can spontaneously generate a cosmos, does that mean some universes arise without any cause at all? Philosophers and physicists alike grapple with this, as it challenges our very notion of how reality operates. Perhaps causality isn't universal, just another rule that applies within our bubble, not beyond it. The quantum fluctuation model doesn't just expand our view of space, it stretches our understanding of existence. If true, it means every moment, somewhere in the infinite froth of reality, new universes are flickering into being, each a roll of the cosmic dice. And that raises one last haunting question. In a multiverse built on randomness, is there any meaning to the fact that we're here at all? Imagine floating in an endless cosmic sea, where every bubble around you isn't just air and water, but an entirely separate universe, complete with its own stars, galaxies, and perhaps even life. This is the essence of the bubble universe hypothesis. a breathtaking vision of reality where our cosmos is just one frothy pocket in an infinite expanse of other universes, each with its own rules. The idea emerges from string theory, which suggests that the fundamental fabric of reality might be woven from tiny, vibrating strings. These strings could arrange themselves in different ways, creating distinct physical laws in each bubble universe. Some might have gravity so weak that matter never clumps into planets, while others could have forces so strong that atoms tear themselves apart instantly. The real kicker, these bubbles aren't static. They drift, expand, and sometimes even collide. If another bubble universe bumped into ours billions of years ago, the shockwave might have left faint ripples in the cosmic microwave background, the afterglow of the Big Bang. Scientists have scoured this ancient light for patterns, like concentric rings or unusual temperature variations, that could hint at such a collision. Some researchers claim to have spotted anomalies that fit the bill, while others dismiss them as cosmic static or measurement errors. The debate rages because if these imprints are real, they'd be the first tangible evidence that we're not alone in the multiverse. But here's the catch: even if bubble universes exist, they might be forever out of reach. Space between them could be stretching faster than light, making collisions vanishingly rare. Worse, the laws of physics in another bubble might be so alien that any signal or structure they produce would be utterly unrecognizable to us. It's like trying to hear a whisper in a hurricane while wearing noise-canceling headphones. Skeptics argue that without a way to test the idea, the bubble universe hypothesis strays into metaphysics. After all, science thrives on evidence, and if something can't be observed or measured, does it belong in the realm of physics or poetry? Yet the idea persists because it solves puzzles that baffle cosmologists. Why does our universe seem so finely tuned for life? If there are infinite bubbles with infinite variations, it's no surprise we find ourselves in one where conditions are just right. It's the ultimate cosmic lottery, and we're the lucky winners. But this also raises a haunting thought. If every possible universe exists, does that make our existence meaningful or just statistically inevitable? The bubble universe hypothesis doesn't just stretch our imagination, it stretches our very sense of place in reality, leaving us to wonder whether we're special or simply one note in an endless cosmic symphony. String theory paints a picture of reality that's both dazzling and dizzying, a cosmic quilt stitched from tiny, vibrating strands of energy. These strings, theorized to be the fundamental building blocks of everything, can vibrate in countless ways, each variation giving rise to different particles and forces. But here's where it gets truly mind-bending. The math suggests there aren't just a few possible configurations, but an almost inconceivable number, a 10 to the power of 500, a figure so vast it dwarfs the number of atoms in our observable universe. This is the so-called landscape of string theory, a sprawling terrain of potential realities where every valley and peak represents a universe with its own unique physics. Now tie this to eternal inflation, and the implications explode. If new universes are constantly bubbling into existence, each could land somewhere different on this landscape, locking in its own set of rules. One universe might have 6 dimensions tightly curled up, another might lack the weak nuclear force, and yet another could have particles that move faster than light. The sheer variety is staggering, but it raises a thorny question. If we can't step outside our universe to explore this landscape, how do we know it's more than a mathematical fantasy? Critics argue that without a way to test these predictions, string theory risks becoming a beautiful castle built in the clouds, elegant but untouchable. Supporters, though, see it differently. They point out that science has always progressed by following math to unexpected places, from black holes to antimatter, long before we could observe them directly. String theory, they argue, might be the same, a roadmap waiting for technology to catch up. Some even propose indirect tests, like searching for signatures of higher dimensions in particle colliders or gravitational waves. But the clock is ticking. After decades of work, the lack of experimental evidence has left some physicists disillusioned, while others double down, convinced that the theory of everything is hiding just beyond our current grasp. The debate cuts to the heart of what science is. Is it enough for a theory to be mathematically consistent, or must it make testable predictions to be taken seriously? String theory's landscape forces us to confront this tension head-on. On one side, there's the awe-inspiring possibility that we've glimpsed the deepest structure of reality. On the other, the gnawing fear that we might be chasing a mirage, lured by equations that describe a universe or multiverse we can never see. Yet for all the controversy, the landscape idea offers something profound, a framework to explain why our universe is the way it is. If every possible set of laws exists somewhere, then ours isn't fine-tuned, it's inevitable. We're not the lucky winners of a cosmic lottery. We're the inevitable inhabitants of a universe that allows us to exist. It's a perspective that's both humbling and liberating, suggesting that the answer to why us might simply be why not. But until we find a way to peek beyond the edges of our cosmic bubble, the string theory landscape remains one of the most tantalizing and contentious ideas in modern physics. What if the Big Bang wasn't a one-time cosmic birth, but just a single heartbeat in an eternal cosmic rhythm? The cyclic multiverse model proposes a breathtaking alternative to the traditional story of creation, one where universes collide, rebound, and regenerate in an endless cosmic dance. Instead of a singular beginning followed by an inevitable heat death, this theory suggests reality is locked in an infinite loop, with each cycle giving rise to a new universe through a titanic collision between cosmic membranes in higher dimensional space. It's a vision of time without end, where destruction and rebirth are two sides of the same cosmic coin. The elegance of this idea lies in how it sidesteps the thorny question of origins. No mysterious singularity or unexplained initial conditions, just an endless cycle of renewal. But this comes with its own set of puzzles. The most glaring is entropy, the universe's tendency toward disorder. If each cycle builds on the last, why hasn't entropy accumulated over infinite time, leaving each subsequent universe more chaotic than the one before? Proponents suggest that when universes collide and rebound, the energy of the collision effectively resets entropy, scrambling the cosmic deck anew. It's like shaking a snow globe so violently that all the flakes settle back into perfect order, a process that strains our current understanding of thermodynamics. Could we ever find evidence for such cycles? Some researchers speculate that gravitational waves from a previous universe's collision might still ripple through space-time, leaving faint imprints in the cosmic microwave background or in future gravitational wave detectors. Others hunt for anomalies in the large-scale structure of the universe, patterns that might hint at a pre-Big Bang phase. But skeptics argue that without a clear mechanism for how information or structure survives from one cycle to the next, the theory remains more poetic than predictive. After all, if each collision erases the slate completely, what difference does infinity make? The cyclic model also grapples with the sheer violence of these proposed collisions. When brane's theoretical higher dimensional objects crash together, the energy released would dwarf anything in nature. Could any structure, even something as vast as a universe, survive such an event intact? Some versions of the theory suggest that the collisions are soft, like two sheets of paper sliding through each other, transferring energy smoothly enough to spawn a new universe without complete annihilation. But this requires fine-tuning that makes some physicists uneasy. What's truly radical about the cyclic multiverse isn't just its reimagining of time, but its challenge to our notion of endings. In this view, heat-death isn't the finale, it's just the prelude to another beginning. No universe dies forever. Instead, each collapse seeds the next creation. It's a vision that resonates with ancient myths of eternal return, yet it's grounded in cutting-edge mathematics. Whether this makes the model profound or merely comforting is up for debate. But one thing's certain, if true, it means the cosmos isn't just expanding, it's breathing. The holographic multiverse turns everything we think we know about dimensions inside out, literally. Imagine the entire cosmos with its swirling galaxies and infinite depths isn't truly three-dimensional at all. Instead, it's a grand illusion, a cosmic mirage projected from information etched on a distant, two-dimensional surface, like a movie playing on a screen we can't see. This isn't science fiction, it's the holographic principle, a radical idea born from the study of black holes and the nature of information itself. When physicists realized that all the data swallowed by a black hole could be perfectly encoded on its event horizon, the point of no return, it sparked a revelation. If information isn't lost inside a black hole but preserved on its surface, could the same be true for our universe? Take this one step further, and you arrive at the holographic multiverse. If our reality is a projection, why couldn't there be others? Some theories suggest multiple universes could be layered like films on the same two-dimensional surface, each encoding a separate three-dimensional world. These holograms might overlap or interact in ways we can't perceive, like shadows cast by different light sources flickering across the same wall. The implications are staggering. If true, it would mean that what we experience as space, time, and even matter are just emergent properties, side effects of deeper, more fundamental processes playing out on a boundary we'll never see. But here's the catch. How could these holographic layers ever influence one another? One possibility is quantum entanglement, that eerie phenomenon where particles remain connected across vast distances. If two universes share the same underlying holographic code, their entangled states might create subtle bridges, hidden threads tying them together. Another idea is that collisions or vibrations on the two-dimensional surface could ripple through multiple projections, causing parallel universes to briefly sync or clash. Picture dropping two pebbles into a pond and watching their waves intersect, except the pond is the fabric of reality itself, and the ripples are entire worlds brushing against each other. Of course, this raises the elephant in the room. Can we ever test such a mind-bending idea? Critics argue that without a way to detect this two-dimensional boundary or measure its projections, the holographic multiverse remains pure mathematics, a beautiful abstraction with no anchor in observable reality. Supporters counter that subtle signatures might lurk in the cosmic microwave background or in the behavior of entangled particles, waiting for the right experiment to reveal them. Others suggest that gravity itself might behave differently on tiny scales if space is truly pixelated, offering a potential window into the hologram's code. What makes this model so provocative isn't just its reimagining of space, but its challenge to our very notion of existence. If we're living in a hologram, then free will, consciousness, and even the passage of time might be secondary phenomena, ephemeral glitches in a deeper, simpler system. It's a humbling thought that the richness of our universe, from supernova to human thought, could be nothing more than data on a cosmic hard drive. Yet it's also oddly unifying, suggesting that at the most fundamental level, all of reality might be written in the same universal language, one we're only beginning to decipher. The holographic multiverse doesn't just expand our horizons, It flattens them, compressing the infinite complexity of existence into a cosmic barcode we can't yet read. Whether this idea will prove to be a stepping stone to deeper truths or a dead end in the quest to understand reality remains to be seen. But one thing's certain: if the universe is a hologram, then the greatest show isn't just playing out in the stars, it's encoded in the fabric of the void itself. What if the universe we experience isn't the base layer of reality, but an elaborate simulation running on some unfathomably advanced computer? The simulation argument takes the multiverse concept into uncharted territory, suggesting that eternal inflation might not just produce natural universes, it could spawn infinite simulated ones. Picture a civilization so technologically mature that they've mastered the ability to recreate entire cosmoses in their machines, tweaking the laws of physics like variables in a cosmic video game. If such beings exist, wouldn't they run countless iterations to study every possible outcome? Suddenly, the idea of bubble universes takes on a whole new meaning. They might not be accidental quantum fluctuations, but deliberate experiments. Proponents of this mind-bending hypothesis point to oddities in our own universe as potential evidence. Take the speed of light, for example. Why does it have that exact value? Could it be a programmed limit like the frame rate of a simulation? Or consider quantum mechanics where particles exist in multiple states until observed. Does this collapse of probabilities resemble the way a computer might render details only when needed to save processing power? Even mathematical constants like pi, which show up everywhere in nature, raise eyebrows. Are these the immutable rules of reality, or just the default settings in some grand cosmic code? But critics push back hard. They argue that calling the universe a simulation is a modern-day god of the gaps, an explanation that sounds scientific but is ultimately untestable. If we can't falsify the idea, they say, it belongs to philosophy, not physics. After all, how would you prove you're not in a simulation? Any evidence you find could itself be part of the program. The debate turns even thornier when you consider that simulated beings, if sufficiently advanced, might create simulations of their own, leading to an infinite regression of nested realities. Where does the chain stop? Is there even a real universe at the bottom, or just turtles all the way down? Yet some scientists aren't ready to dismiss the idea entirely. They propose hypothetical tests, like searching for computational pixelation in the fabric of space-time at unimaginably small scales. Others suggest that high-energy particle collisions might reveal energy limits or rounding errors, glitches in the cosmic matrix. So far, no such anomalies have been found, but the search continues. What makes the simulation argument so provocative isn't just its technological twist on creation, it's the existential vertigo it induces. If we're living in someone else's experiment, does that make our joys, struggles, and discoveries any less real? Or does it force us to confront the unsettling possibility that reality might be more malleable and more mysterious than we ever dared to believe? The simulation hypothesis doesn't just blur the line between science and science fiction. It erases it entirely, leaving us with a haunting question. If the multiverse is real, could it be someone else's masterpiece? And if so, what does that make us, the explorers or the explored? In the swirling chaos of an infinite multiverse, where random fluctuations can birth entire universes, something even stranger might emerge, a lone, self-aware mind floating in the void, conjured into existence by pure chance. This is the bizarre premise of the Boltzmann brane paradox, named after the 19th century physicist Ludwig Boltzmann, who first grappled with the eerie implications of statistical mechanics. Imagine a universe so vast and old that even the most improbable events become inevitable. Given enough time, quantum jitters could theoretically assemble particles into a functioning brane, complete with false memories of a past that never happened. Not a body, not a world, just a disembodied consciousness hallucinating an entire reality. Now here's the twist. If Boltzmann brains are possible, they should vastly outnumber evolved beings like us. After all, assembling a single brain by accident requires infinitely less energy and time than crafting a universe with galaxies, planets, and life over billions of years. So statistically speaking, the odds favor you being a Boltzmann brain right now, momentarily convinced you're reading this script rather than a flesh and blood person in a real cosmos. It's a cosmic gut punch to our sense of reality, one that forces us to question whether our memories, our scientific observations, even our perception of time, are just fleeting illusions. Physicists recoil from this idea not because it's impossible, but because it renders science meaningless. If most minds in the multiverse are Boltzmann brains hallucinating inconsistent realities, how could we trust any observation or experiment? The periodic table, the fossil record, the cosmic microwave background, all could be elaborate fabrications of a mind that blinked into existence 5 minutes ago. Some theorists try to sidestep the paradox by arguing that universes capable of producing Boltzmann brains must be so rare or unstable that they cancel themselves out. Others suggest that the very act of questioning our reality might be evidence against it. After all, a Boltzmann brain would lack the consistent environment needed to develop logic or science. But the paradox lingers because it exposes a fault line in our understanding. Cosmology tells us the universe tends toward disorder, yet here we are, ordered beings in an ordered cosmos, seemingly defying the odds. Either we're astronomically lucky, or our theories about the multiverse are missing something fundamental. The Boltzmann brain dilemma isn't just a thought experiment. It's a litmus test for whether our models of reality can account for the very observers trying to make sense of them. At its core, this isn't just about physics, it's about the nature of existence itself. If consciousness can emerge from chaos, does that make it more or less miraculous? Are we the intended outcome of cosmic evolution, or just a fleeting statistical blip? The Boltzmann brain paradox doesn't offer answers, but it forces us to stare into the abyss of our assumptions, leaving us to wonder, in an infinite multiverse, what does it even mean to be real? The universe seems suspiciously well-suited for life. Gravity isn't too strong, the cosmological constant isn't too large, and the fundamental forces balance perfectly to allow atoms, stars, and eventually conscious observers like us to exist. This eerie precision is what physicists call the fine-tuning problem, and it's one of the most perplexing mysteries in cosmology. Enter the Anthropic Principle, a controversial idea that shifts the question from why is our universe so perfectly tuned to what else could we possibly observe? The logic is simple. In a multiverse teeming with countless universes, each governed by random physical constants, only those rare pockets where conditions happen to allow life will ever have observers to ponder their own existence. We don't live in a special universe, we live in the only kind of universe where beings like us could arise to notice it at all. But here's where the debate ignites. Detractors argue that the Anthropic Principle is less an explanation and more a philosophical shrug, a way to dismiss the fine-tuning problem without truly solving it. If every possible universe exists, they say, then invoking the Anthropic Principle is like marveling at how perfectly your lottery numbers match the winning ticket while ignoring the millions of other tickets that lost. Supporters counter that this misses the point. The principle isn't meant to explain why our universe exists. It's a tool to explain why we perceive it the way we do. In this view, fine-tuning isn't a puzzle to solve but a selection bias to acknowledge, a cosmic version of survivor's bias. where the winner's life-permitting universes are the only ones visible in the data. The tension here isn't just scientific, it's deeply philosophical. Does the Anthropic Principle elevate the multiverse from a speculative idea to a necessary framework for understanding our place in reality? Or does it reduce physics to a kind of cosmic storytelling, where inconvenient questions are hand-waved away with statistics? Some theorists propose middle grounds, suggesting that while the multiverse might explain fine-tuning, it doesn't rule out deeper, underlying laws that favor life-friendly universes in the first place. Perhaps certain constants aren't random but emerge from a more fundamental theory we haven't yet uncovered, a theory that, even in a multiverse, nudges reality toward habitability. What makes this debate so electrifying is how it forces us to confront the limits of science itself. If the Anthropic Principle holds, then cosmology becomes a strange loop. The very act of observation shapes what we can meaningfully say about the universe. It's as if the cosmos is a hall of mirrors where the presence of observers bends the reflection of reality. But if the principle falls short, then fine-tuning remains a glaring anomaly, a cosmic just right that demands an answer beyond chance. Either way, the Anthropic Principle doesn't just challenge how we see the multiverse, it challenges how we see ourselves. Are we the improbable winners of a cosmic lottery, or the inevitable outcome of a reality that, in some deep way, was always meant to be noticed? The answer, much like the multiverse itself, might be stranger than we imagine. The moment you flip a coin, the universe doesn't just wait to see if it lands heads or tails. It splits in two, with one reality where it comes up heads and another where it's tails. This is the startling promise of the many worlds interpretation, a radical take on quantum mechanics that suggests every possible outcome of every quantum event actually happens, just in a separate, branching universe. Forget Schrödinger's cat being both alive and dead in a box. In this view, there's one universe where the cat purrs happily and another where it meets its tragic end, and neither is aware of the other. But here's where it gets even wilder. Some theorists propose that these branching paths don't just exist as abstract possibilities, but as full-fledged universes, each born from the same cosmic process that drives eternal inflation. How does this branching actually work? Picture a river dividing into countless streams, each carving its own path through the landscape. At the quantum level, particles exist in a haze of probabilities, a state called superposition, until something interacts with them, forcing a collapse into a definite state. Traditional physics says this collapse is random, but many worlds argues there's no collapse at all. Instead, the universe fractures, with every possible outcome playing out in its own timeline. The math behind this is surprisingly elegant, treating the entire cosmos as a wave function that never stops evolving, never discards possibilities. It just keeps branching. But if reality splits so easily, why don't we notice? Why can't we catch a glimpse of these parallel versions of ourselves? The answer lies in decoherence, a kind of quantum amnesia where branching worlds rapidly lose the ability to interact. Think of it like two radio stations broadcasting on nearly identical frequencies. At first, you might hear static where they overlap, but as they drift apart, the signals no longer interfere. In the same way, branching universes become invisible to one another almost instantly, their histories diverging too sharply for any crossover. That raises the ultimate question. If these worlds can't touch or communicate, how could we ever prove they exist? Some physicists point to subtle anomalies in quantum experiments, statistical fingerprints that might hint at interactions with parallel realities. Others suggest that gravity, the only force thought to transcend dimensions, could carry faint echoes between branches. But for now, the evidence remains frustratingly out of reach, leaving many worlds in a strange limbo, mathematically sound, philosophically profound, yet experimentally unverified. What makes this idea so compelling and controversial is how it reshapes our understanding of choice and chance. In a multiverse of branching worlds, every decision you've ever made has a counterpoint somewhere else. The job you didn't take, the person you didn't meet, the road you didn't walk, they're all real, just not in this version of reality. It's a concept that's equal parts exhilarating and unnerving, suggesting that the universe isn't just stranger than we imagine, but stranger than we can imagine. And that leaves us with one last haunting thought. If every possibility exists somewhere, does that make our lives more meaningful, or just one thread in an infinite tapestry of what-ifs? Imagine our universe isn't a lonely island in the void, but a slice of something far grander, a cosmic membrane drifting through a hidden ocean of higher dimensions. This is the brane multiverse, a vision of reality so audacious it reshapes everything we think we know about space and time. In string theory's most daring models, what we perceive as our three-dimensional universe might just be one of many branes, short for membranes, floating like sheets of paper in an 11-dimensional expanse. Each of these branes could harbor its own stars, galaxies, and even life, operating under laws of physics completely alien to ours. The kicker, these parallel worlds might be closer than we think, separated by dimensions so tightly curled we'd never notice them until they collide. The real showstopper of this model is how it reimagines the Big Bang itself. Forget a singularity exploding from nothing. Picture two branes, each a universe in its own right, smashing together with unimaginable force. The energy of that collision wouldn't just create a new universe, it would birth an entire cosmic epoch, resetting the clock and scattering the seeds of galaxies. It's a cyclical vision of creation, where universes don't just expand and fade but collide, rebound, and regenerate in an endless cosmic dance. Some theorists even suggest this could explain the eerie uniformity of our universe's background radiation, the afterglow not of a single Big Bang, but of a brane collision so violent it smoothed out all wrinkles in space-time. But here's the rub. If these extra dimensions exist, why can't we see or feel them? The math suggests they might be microscopically small, curled up like the fibers of a carpet, visible only to particles at energies we can't yet produce. Others propose that gravity, unlike other forces, could leak between branes, explaining why it's so weak compared to electromagnetism or the nuclear forces. Imagine gravity as a ripple in a pond. Most of its energy stays in the water, but a tiny fraction escapes into the air. If our brane is the water's surface, gravity's faintness might just be evidence of its journey through dimensions we can't access. Skeptics aren't convinced. Without experimental proof of extra dimensions or brane collisions, they argue the theory is little more than a beautiful equation with no anchor in reality. The Large Hadron Collider has hunted for signs of these hidden dimensions like particles vanishing into them or unexpected energy spikes, but so far, the detectors have stayed silent. Even the cosmic microwave background, our most detailed snapshot of the early universe, shows no definitive scars from brane collisions. Yet the brane multiverse persists because it solves puzzles other theories can't. Why does the universe appear fine-tuned for life? If countless branes exist with random physical laws, we'd naturally find ourselves in one that allows our existence. How did inflation start? A brane collision could have kickstarted it, like a pebble dropped into a still pond. And what lies beyond our cosmic horizon? Perhaps not emptiness, but other branes, alternate realities hovering just beyond our perception. What makes this idea so thrilling and frustrating is how it balances on the knife edge of science and speculation. The math works, but the universe hasn't handed us the evidence yet. Until it does, the brane multiverse remains a tantalizing what-if, a reminder that reality might be stranger than our boldest dreams. And if one day we do find proof, it would mean our universe isn't just one among many. It's one layer in a cosmic stack pressed between worlds we're only beginning to imagine. The mystery of dark energy isn't just a puzzle, it's the invisible hand shaping the fate of the entire multiverse. Picture a force so powerful it's tearing space itself apart, accelerating galaxies away from each other faster and faster, yet so subtle we didn't even know it existed until the late 1990s. This is the enigma at the heart of eternal inflation. Dark energy doesn't just influence our universe's expansion, it might be the engine that fuels the creation of countless others. But here's the twist, we still don't know whether dark energy is a constant, unchanging presence, like a cosmic background hum, or a dynamic force that waxes and wanes over time. The answer could rewrite everything we think we know about the multiverse. Take our own universe as an example. If dark energy were just slightly stronger, galaxies would have been ripped apart before stars could even form, leaving the cosmos a vast, empty wasteland. Slightly weaker, and gravity would have pulled everything back into a crushing big crunch eons ago. The fact that we exist in this narrow sweet spot feels like winning the cosmic lottery, unless, of course, there are infinite universes out there with every possible value of dark energy, and we just happen to live in one where the numbers lined up right. This idea, known as the dark energy landscape, suggests that what we perceive as fine-tuning might just be a statistical inevitability in a multiverse where every scenario plays out. Yet the plot thickens when you consider alternative models. Some theories propose that dark energy isn't a fixed property of space but a field that evolves, growing stronger or weaker over time. In certain universes, it might flare up violently, shredding matter apart in a phantom-like Big Rip. In others, it could fade into irrelevance, allowing gravity to dominate and collapse everything back into a singularity. If eternal inflation is real, these variations could mean that bubble universes aren't just different in their laws of physics. They might live and die by entirely different cosmic clocks, some expanding into eternity, others snuffed out in an instant. The real challenge, dark energy, is notoriously elusive. Unlike matter or radiation, it doesn't clump, reflect, or emit light. We only infer its existence by watching how galaxies move, like detectives piecing together a shadow's shape by the way it bends the light around it. Current telescopes can map its effects, but to understand its true nature, we'd need to catch it in the act of changing, a feat that might require observing the universe over billions of years, or detecting subtle shifts in the fabric of space-time itself. Until then, theories about its role in eternal inflation remain tantalizing but unproven, caught between mathematical elegance and observational silence. What makes this more than just academic curiosity is the existential stakes. If dark energy isn't constant, our universe's fate might not be the quiet fade into darkness we assume. It could end in a catastrophic rupture or an unexpected rebirth. Even more unsettling, if dark energy's value can vary across universes, does that mean the multiverse is a chaotic laboratory where most experiments fail, and we're just lucky enough to witness one that succeeded? The enigma of dark energy doesn't just challenge our understanding of physics. It forces us to confront whether our universe is a deliberate masterpiece or a random stroke of cosmic luck. And until we solve it, the multiverse remains a story with its most crucial chapter still unwritten. Every cosmic story has to start somewhere, but what if the origin of eternal inflation isn't just a mystery, but a question that threatens to unravel the very foundations of science? The initial conditions problem cuts to the heart of cosmology. What set this infinite chain reaction of universe creation into motion? Picture a row of dominoes falling endlessly, but who placed the first one? Some theories suggest a quantum nucleation event, a spontaneous flicker in the fabric of reality where a tiny bubble of false vacuum tunneled into existence, triggering inflation like a match tossed into dry tinder. In this view, our multiverse might have emerged from sheer randomness, a statistical fluke in an otherwise featureless void. But randomness alone doesn't satisfy everyone. Another camp argues for a pre-existing multiverse, an eternal, perhaps cyclical meta-reality where inflation isn't the beginning but just another phase in an unfathomably ancient sequence. Imagine a cosmic conveyor belt endlessly recycling universes, each one born from the ashes of its predecessor. This sidesteps the need for a singular starting point, but it raises an even thornier question. If the multiverse has always existed, what explains its existence? The moment you try to answer, you're caught in an infinite regress, a hall of mirrors where every explanation demands another explanation behind it. The frustration here isn't just philosophical, it's a fundamental limit of our scientific tools. Physics excels at describing how things happen, but stumbles when asked why they began. Even the concept of before the Big Bang might be meaningless, like asking what's north of the North Pole. Some theorists propose radical solutions, like the idea that time itself is emergent, crystallizing only after inflation begins. Others speculate that the laws of physics aren't fixed but evolve, meaning the initial conditions might not need an external cause. They could be self-configuring, like a puzzle that solves itself. Yet the most provocative possibility is that we're asking the wrong question entirely. What if the initial conditions aren't something to be explained, but a brute fact, a foundational feature of reality with no deeper cause? After all, science has always progressed by accepting certain axioms: gravity just is, electrons just spin, and building upward. Could the same be true for the birth of the multiverse? Or does accepting that mean surrendering to mystery? The search for answers is pushing physicists into uncharted territory. Some are exploring loop quantum gravity, where the singularity of the Big Bang is replaced by a bounce from a previous universe. Others toy with holographic models, where the three-dimensional universe is a projection of information encoded on a two-dimensional surface, making the question of initial conditions a kind of cosmic optical illusion. And then there's the most radical notion of all, that causality itself might be an illusion, a local quirk of our universe rather than a universal law. What's at stake isn't just the origin of universes, but the limits of human understanding. If eternal inflation is true, then science might never reach a first cause, only an endless chain of hows. But that doesn't have to be a defeat. After all, the beauty of the multiverse isn't just in its answers, it's in the questions it forces us to confront about the nature of reality, time, and our place in the grand scheme of things. Whether we're standing at the edge of a cosmic waterfall or caught in an eternal cycle, one thing's certain: the journey to understand it is far from over. The cosmic microwave background isn't just a relic of our universe's fiery birth, it's a potential message board for the multiverse, etched with faint clues that might reveal our cosmic neighbors. Imagine it as the universe's baby photo, a snapshot of the sky just 380,000 years after the Big Bang, when the cosmos cooled enough for light to break free. But peer closely, and this seemingly uniform glow holds tiny irregularities, whispers of density variations that seeded galaxies. Some researchers argue that hidden among these subtle fluctuations might be something far stranger: the fingerprints of other universes brushing against our own. Take the infamous cold spot, a mysterious region in the CMB that's significantly chillier than its surroundings. One explanation is that it's a cosmic bruise, evidence of a collision with another bubble universe long ago. Think of it like a dent in a car fender, a remnant of a fender bender with another vehicle in the cosmic parking lot. The math suggests such collisions would create distinct patterns, concentric rings of temperature variation, or abrupt edges in the CMB's texture. A few teams claim to have spotted these anomalies, but the debate rages. Are they truly glimpses of the multiverse, or just statistical flukes, cosmic static masquerading as a signal? Skeptics aren't convinced. They point out that the cold spot could just as easily be a vast cosmic void, a region of space unusually empty of galaxies, stretching the light passing through it and cooling the CMB in that direction. Others argue that the human brain is wired to find patterns, even in randomness, and that we're seeing phantom messages in the noise. After all, if you stare at static long enough, you might start imagining faces. The challenge is separating true anomalies from the cosmic equivalent of a Rorschach test. Yet the hunt continues because the stakes couldn't be higher. If even one of these anomalies holds up, it would shatter our understanding of reality, proving we're not alone in the multiverse. Future telescopes, like the European Space Agency's Euclid or NASA's upcoming SPHEREX, could settle the debate with unprecedented precision, mapping the CMB's faintest ripples in search of telltale distortions. But until then, these tantalizing hints remain in limbo, teasing us with the possibility that our universe might be just one page in a vast cosmic library, its edges subtly warped by the weight of others pressing close. What makes this search so electrifying isn't just the science, it's the sheer audacity of the idea. We're not just studying our universe, we're forensic investigators, sifting through ancient light for traces of realities beyond our own. And whether the clues pan out or fade into noise, the quest itself reshapes how we see the cosmos, not as an island, but as a shore where countless unseen waves might be lapping at the edges of perception. What if the universe isn't just described by mathematics? What if it is mathematics? Max Tegmark's mathematical universe hypothesis takes the multiverse to its logical extreme, proposing that every possible mathematical structure isn't just a tool for understanding reality, but reality itself. In this mind-bending view, eternal inflation isn't merely spawning bubble universes with varying physical laws, it's generating every conceivable mathematical configuration, each one a self-contained cosmos. Picture a cosmic library where every book isn't just a story, but an entire universe, its narrative written in equations rather than words. Your morning coffee, the spiral of a galaxy, even the sensation of déjà vu, all could be mathematical patterns playing out in a structure we happen to inhabit. But how does abstract math translate into the tangible world we experience? Think of numbers as the raw material of existence. Just as a symphony emerges from specific arrangements of notes, our universe might arise from a particular mathematical shape or equation. Some configurations could manifest as four-dimensional spaces with quantum fields, while others might resemble fractal labyrinths or hyperdimensional geometries beyond human comprehension. The haunting implication: we don't live in a universe governed by math, we live inside the math. It's like discovering that the characters in a novel aren't following the rules of grammar, they're made of letters themselves. This raises a glaring question. Why do we perceive only one coherent set of physical laws? If all mathematical structures exist equally, shouldn't we be aware of the more chaotic or inconsistent ones? Tegmark suggests a form of cosmic natural selection. Only self-aware observers can arise in structures stable enough to support complexity. A universe where logic fluctuates randomly might not allow particles to form atoms, let alone brains capable of questioning reality. So while infinite mathematical worlds exist, we're naturally trapped in one where the equations add up to conscious experience, a Goldilocks zone of computability. Critics push back hard, arguing that the hypothesis strays into metaphysics. If every mathematical object is equally real, how do we explain the apparent uniqueness of our universe's history? Why does this particular math feel so concrete while others remain theoretical? Some physicists counter that the hypothesis isn't falsifiable, a cardinal sin in science, while others see it as an inevitable conclusion of taking mathematics seriously as the foundation of reality. After all, quantum mechanics already treats particles as probability waves described by equations. Is it such a leap to say the equations are the waves? The mathematical universe hypothesis doesn't just challenge our view of cosmology, it redefines existence itself. If true, it means the multiverse isn't a chaotic zoo of random physics, but a perfectly ordered and infinite collection of logical structures. No cosmic accidents, no arbitrary constants, just the inevitable unfolding of all possible mathematics. And that leaves us with a humbling thought. Perhaps we're not just discovering the laws of the universe. We might be discovering the only laws we're capable of perceiving, while the rest of mathematical reality hums quietly beyond our grasp, vast and silent as a theorem waiting to be solved. The second law of thermodynamics feels like the universe's strictest accountant. It insists that disorder must always increase, that entropy marches irreversibly toward chaos. Yet eternal inflation seems to break the rules, endlessly spawning fresh new bubble universes like pristine sheets of paper rolling off a cosmic printing press. Each one starts with remarkably low entropy, a perfectly ordered state that defies the usual trend toward randomness. How can this endless production of tidy new universes square with the law that demands everything must eventually decay into disorder? It's as if the universe found a loophole in its own rulebook, and physicists are locked in a fierce debate over whether that loophole is real or whether we're missing something fundamental. One possible resolution hides in the fine print of entropy itself. While each newborn bubble universe might appear orderly, the total entropy of the multiverse could still be increasing if the space between these bubbles grows ever more chaotic. Picture a sprawling mansion where every new room is immaculately cleaned, but the hallways connecting them become increasingly cluttered with dust and debris. From the perspective of someone inside a single room, things seem tidy, but step back and the overall mess is undeniable. In this view, the entropy of the entire system still rises, even as local pockets temporarily defy the trend. Others argue for more radical solutions. Perhaps the second law isn't universal, maybe it only applies to closed systems, and eternal inflation operates on a scale so vast that the usual rules don't hold. Think of gravity. On Earth, it pulls apples downward predictably, but near a black hole, its behavior warps beyond recognition. Could entropy work similarly, bending or even breaking in the seething quantum foam where new universes are born? Some theorists speculate that the very act of bubble nucleation resets entropy, like a cosmic etch-a-sketch being shaken clean with each new universe. Then there's the unsettling possibility that we're asking the wrong question entirely. What if entropy isn't the immutable law we think it is, but an emergent property, a side effect of how we perceive time and causality? In quantum mechanics, particles can temporarily decrease entropy through rare fluctuations, a phenomenon that might scale up in the frenzied environment of eternal inflation. If countless universes are constantly popping into existence, statistical inevitability suggests some will emerge improbably ordered, like a deck of cards shuffling itself into perfect suit order by pure chance. The stakes here aren't just academic. If eternal inflation truly violates thermodynamics, it could mean our understanding of physics is incomplete, that some deeper principle governs the birth of universes, one that reconciles infinite creation with inevitable decay. Or it might reveal that entropy isn't the final word on disorder, but a local feature of our cosmic neighborhood. Until we solve this conundrum, eternal inflation remains both a dazzling vision of reality's abundance and a nagging puzzle that challenges the very laws we thought were unbreakable. One thing's certain, in a multiverse where the rules themselves might be up for debate, the only constant is the thrill of the unknown. Quantum mechanics has always flirted with the bizarre idea that observation shapes reality. Think of Schrödinger's cat, neither alive nor dead until someone opens the box. But what if this strange principle doesn't just apply to subatomic particles in a lab, but to the entire multiverse? Some theories propose that conscious observers don't just measure reality, they somehow select which branches of the multiverse become tangible, like a cosmic gardener pruning an infinite tree of possibilities. It's a notion that blurs the line between physics and philosophy, suggesting that the universe might not just exist independently, but requires witnesses to bring it into focus. Where does this idea come from? Look no further than the infamous measurement problem in quantum mechanics. When particles exist in superpositions, multiple states at once, what causes them to collapse into a single outcome upon observation? The traditional Copenhagen interpretation shrugs and says this is just how the math works, but alternative views like von Neumann-Wigner interpretation take it further, proposing that consciousness itself triggers the collapse. Extend this to eternal inflation, and you get a staggering implication. Bubble universes might remain in ghostly superposition until an observer chooses one, like tuning a radio to a specific station out of infinite static. Critics recoil at this, calling it a slippery slope back to pre-scientific mysticism, where the mind dictates cosmic structure. They argue there's no known mechanism for consciousness to influence quantum events, let alone universe-scale physics. If observation requires a living observer, does that mean the early universe devoid of life existed in a hazy, unrealized state? It's a paradox that leaves even proponents scratching their heads. Some attempt to sidestep it by redefining observation as any interaction that leaves a measurable record, like photons bouncing off atoms, but that dilutes the original claim's boldness. Yet the idea persists because it tackles uncomfortable gaps in our understanding. Why does the universe seem finely tuned for life? If observers select habitable realities, it's no longer a coincidence, it's a self-fulfilling prophecy. This line of thinking, dubbed the participatory anthropic principle, suggests that the multiverse isn't a static landscape but an interactive one, where observation and existence are two sides of the same coin. It's as if reality is a grand orchestra and consciousness is the conductor, silently shaping the music by the mere act of listening. The debate rages because it cuts to the core of what science is. If consciousness plays an active role in cosmology, does that elevate the mind to a cosmic force, or does it confuse the map with the territory? Some physicists dismiss it as untestable speculation, while others see it as the next frontier, a bridge between quantum weirdness and the vastness of the multiverse. One thing's certain, in a cosmos where observation might shape reality, the act of searching for answers could itself be part of the mystery. Black holes aren't just cosmic vacuum cleaners, they might be cosmic mothers, giving birth to entirely new universes hidden within their crushing depths. This startling idea, championed by physicist Lee Smolin, flips our understanding of cosmic evolution on its head. Picture a black hole's singularity, that point of infinite density where space and time break down, not as a dead end but as a gateway. When matter collapses beyond the event horizon, the theory suggests, the extreme conditions could trigger a new Big Bang, rebooting reality with slightly tweaked physical constants. In this wild vision, every black hole in our universe might contain a fledgling cosmos, expanding unseen within its own space-time bubble, completely disconnected from our own. Boltzmann takes this further with his provocative theory of cosmological natural selection. Just as biological evolution favors organisms that reproduce successfully, he argues universes could evolve to maximize black hole production. Each offspring universe inherits slightly altered laws of physics from its parent. Some changes help spawn more black holes, others hinder it. Over countless generations, universes that produce the most black holes would dominate the multiverse landscape, explaining why our cosmos seems fine-tuned for black hole formation. It's cosmic Darwinism on the grandest scale, survival of the fecund. But where's the evidence? Critics pounce on this gap, arguing that without observable traces of these offspring universes, the theory remains speculative poetry. Boltzmann counters with an intriguing prediction. If his model holds, the laws of physics should be optimized for black hole creation. Surprisingly, our universe checks several boxes. Neutron stars hover just below the mass threshold needed to collapse into black holes, and supernova occur at rates that maximize stellar black hole formation. Even the cosmological constant, that mysterious number driving the universe's expansion, sits at a value that allows galaxies, and thus black hole factories, to form without being ripped apart too quickly. The debate gets thornier when we consider what happens inside a singularity. Classical physics breaks down at this point, leaving quantum gravity as the only potential guide, and we still lack a complete theory to describe it. Some models suggest singularities might bounce, transforming collapse into explosion via quantum effects. Others propose that black holes don't form true singularities at all, but rather Planck-scale nuggets of spacetime where new physics takes over. Without knowing what truly occurs at a singularity's core, the black hole multiverse remains a breathtaking hypothesis waiting for experimental validation. What makes this idea so compelling and controversial is how it reframes the multiverse. Rather than an aimless froth of random bubbles, Boltzmann's vision presents a lineage, a cosmic family tree where universes pass on their traits. It turns black holes from destroyers into creators, offering a profound twist on the cycle of cosmic death and rebirth. Whether the math ultimately supports this radical reimagining or not, it forces us to confront a humbling possibility. We might be living in just one generation of an infinite cosmic dynasty, our black holes quietly incubating universes we'll never see. Time's arrow seems obvious to us. Eggs crack but never uncrack, memories form but don't unform, and the universe expands rather than contracts. But peel back the layers, and this one-way flow of time becomes one of physics' greatest puzzles. At the microscopic level, the laws of physics are almost entirely time-symmetric. They work just as well whether time runs forward or backward. So why does our lived experience feel so stubbornly irreversible? The answer might lie not in the laws themselves, but in the chaotic, sprawling landscape of eternal inflation and its multiverse. Imagine flipping a coin in a universe where time runs backward. Heads becomes tails, smoke pours into cigarettes, and shattered glasses leap back onto tables intact. Such a reality isn't just possible in the multiverse, it might be inevitable. Some bubble universes could emerge with entropy decreasing rather than increasing, creating a world where time's arrow points in reverse. Others might loop like a Möbius strip, with cause and effect folding back on themselves endlessly. But here's the catch. Conscious observers like us can only exist in universes where time's direction aligns with increasing entropy. Why? Because complexity, life, thought, even perception requires the irreversible buildup of structure from chaos. In a universe where time flowed backward, your brain would constantly unravel, your memories dissolving before they could form. You'd never notice, of course, because you couldn't exist to witness the paradox. This leads to a startling realization. Our experience of time might not be a universal truth, but a selection effect. Eternal inflation could spawn countless universes with every conceivable arrow of time, but only those where entropy consistently grows would ever harbor observers to ponder the question. It's like a cosmic version of survivorship bias. We don't see the universes where time behaves strangely because they're inhospitable to life by definition. Some theorists take this further, suggesting that the Big Bang's low entropy state wasn't a fluke, but a necessity. If the multiverse is a vast entropy factory, our universe's orderly beginning might just be the rare edge case where structure could emerge at all. Yet mysteries linger. If other arrows of time exist beyond our bubble, could we ever detect them? One tantalizing clue might lie in the cosmic microwave background. Certain anomalies, like large-scale asymmetries in temperature, could hint at collisions with universes where time runs differently, leaving scars in the fabric of our reality. Another possibility is that black holes, those cosmic one-way streets, act as portals to regions of reversed time, though this remains speculative. For now, the arrow of time stands as both a cornerstone of our existence and a humbling reminder that what we perceive as fundamental might just be a local quirk in an infinitely stranger multiverse. The deeper we dig, the more time's arrow reveals itself not as a law but as a story, one written by the peculiar conditions of our cosmic neighborhood. In the grand tapestry of eternal inflation, universes might flicker in and out of existence with every conceivable flow of time, like candles burning at both ends or in spirals we can't fathom. And that leaves us with a haunting question. If time's direction isn't fixed, could the multiverse hold realities where past and future are just points on a circle, or where cause and effect dance in an endless, unpredictable loop? The answer, much like time itself, remains just out of reach. The idea of a multiverse captivates the imagination, but does it hold up under scientific scrutiny? Critics raise a crucial point: extraordinary claims require extraordinary evidence, and so far, no telescope or particle detector has delivered irrefutable proof of other universes. This is the null hypothesis challenge in its purest form. Until data forces us to think otherwise, shouldn't we default to the simplest explanation that our universe is all there is? It's a principle as old as science itself, echoing Occam's razor, the idea that among competing hypotheses, the one with the fewest assumptions should be selected. From this perspective, invoking an infinite number of unseen universes to explain the quirks of our own might seem like intellectual sleight of hand, a way to dodge tough questions about fine-tuning or cosmic origins. But the debate isn't just about philosophy, it's about the boundaries of science itself. For a theory to be scientific, it must make testable predictions. Can eternal inflation meet that bar? Supporters point to potential signatures in the cosmic microwave background or anomalies in large-scale galaxy distribution that could hint at collisions with other bubble universes. Detecting such signals would be groundbreaking, but skeptics counter that these are speculative at best. Without a definitive observation, they argue, the multiverse remains in the realm of metaphysics, not physics. It's like claiming there's an invisible dragon in your garage. If no experiment can reveal it, is the idea meaningful or just a creative thought experiment? The tension here reveals a deeper rift in cosmology. Some physicists, like Nobel laureate Roger Penrose, argue that resorting to a multiverse is a surrender, a way to explain away fine-tuning without digging for deeper laws that might govern our single universe. Others, like Sean Carroll, counter that the multiverse isn't an escape from science but an extension of it, a natural consequence of well-established theories like inflation and quantum mechanics. The disagreement isn't just academic, it's about how far we should let math guide us into the unknown. After all, history is full of ideas, from black holes to the Big Bang, that seemed outlandish until evidence caught up. Yet the burden of proof remains heavy. Even if the math behind eternal inflation is elegant, science demands more than equations, it demands verification. Some researchers propose creative workarounds, like searching for indirect effects of other universes on quantum entanglement or gravitational waves. Others admit that concrete evidence might forever lie beyond our observational horizon, locked away by the sheer scale of cosmic inflation. That possibility forces a tough question. If a theory can't be tested, even in principle, does it belong in science at all? What makes this debate so vital is that it's not just about universes, it's about the soul of scientific inquiry. Are we willing to entertain ideas that stretch beyond our current tools, or should we demand immediate empirical grounding? The answer might lie in balance, a willingness to explore the multiverse as a compelling hypothesis while acknowledging that, for now, it remains a breathtaking possibility waiting for its moment of proof. Until then, the cosmos keeps its deepest secrets close, challenging us to wonder without ever quite letting go of doubt. The fine-tuning of our universe is so precise it borders on the uncanny. Alter gravity by a fraction, tweak the strength of the nuclear forces ever so slightly, and stars wouldn't form, atoms wouldn't bond, and life as we know it would be impossible. For some, this precision suggests a cosmic architect, a divine hand that set the dials just right. But the multiverse theory offers a radically different explanation. If infinite universes exist with every possible configuration of physical constants, then of course we find ourselves in one where the numbers lined up perfectly. No designer required just the brute force of statistical inevitability. This clash between theology and cosmology isn't just academic. It cuts to the heart of how we understand existence itself. Yet the debate doesn't end there. If the multiverse is the answer to fine-tuning, what fine-tuned the multiverse? Why does it spawn universes at all, let alone ones capable of harboring life? Some philosophers argue this just kicks the can down the road. Instead of a designer fine-tuning one universe, you might need a meta-designer fine-tuning the mechanism that spawns universes. It's like finding a perfectly crafted watch on a beach and arguing it washed up from a factory that randomly produces infinite watches. Sure, given enough time, one would turn out functional, but who built the factory? Theologians see this as a backdoor for the divine, a way for a creator to operate on a scale even grander than a single cosmos. Scientists counter that the multiverse could be self-sustaining, requiring no deeper cause, just as the Big Bang might not need a before. The tension here isn't just about evidence, it's about the limits of explanation. Science excels at describing how things work, but stumbles when asked why they exist in the first place. The multiverse might explain fine-tuning without invoking God, but it doesn't answer why there's something rather than nothing. Some physicists, like Stephen Hawking, famously argued that the laws of gravity alone could bring universes into being from nothing, making a creator superfluous. Others, like physicist Paul Davies, retort that this merely replaces one mystery with another. Why does gravity exist with precisely the properties needed to spawn universes? The conversation spirals into metaphysics, where science and philosophy blur. What makes this controversy so gripping is how it forces us to confront the boundaries of human understanding. Can science ever truly answer the why of existence, or is that a question forever beyond its scope? Some researchers propose a middle path, suggesting that if the multiverse is real, it might not eliminate the need for a deeper principle, a theory of everything that explains why the multiverse behaves as it does. This wouldn't necessarily point to a traditional deity, but to an ultimate law or logic underlying all realities. Others argue that asking why at all is a category error, like a character in a video game questioning why the game's code exists. The rules simply are, and the universe or multiverse just plays them out. The fine-tuning controversy doesn't just challenge our theories, it challenges our very sense of meaning. If we're here by cosmic accident, does that make life more precious or more absurd? If the multiverse is a divine creation, does that resolve the mystery or deepen it? These aren't questions science can answer alone, but they're impossible to ignore. Whether the multiverse renders God unnecessary or demands an even grander designer, one thing's certain: the universe's fine-tuning isn't just a puzzle for physicists. It's a mirror reflecting our deepest questions about existence, purpose, and whether the cosmos is ultimately friend, foe, or simply indifferent. And that's a mystery no theory, no matter how elegant, can fully dissolve. At the heart of eternal inflation lies a gaping hole in our understanding, a chasm where known physics dissolves into uncertainty. The theory hinges on conditions so extreme that even Einstein's relativity and quantum mechanics, the twin pillars of modern physics, crumble under the strain. This is the quantum gravity gap, the missing link between the universe we observe and the speculative frenzy of the multiverse. Without a theory that unifies gravity with quantum mechanics, eternal inflation rests on a foundation of untested assumptions, like trying to build a skyscraper with blueprints that stop at the third floor. Consider the moment of cosmic inflation's inception, a realm of unimaginable density where space-time itself flickers in and out of existence. Here, gravity isn't just a force, it's a quantum phenomenon, warping reality on scales 1 trillion times smaller than an atom. Yet our equations go dark in this regime. General relativity paints gravity as the curvature of smooth space-time, while quantum mechanics insists everything is granular, pixelated. When these two visions collide in the early universe, the result isn't clarity, it's mathematical chaos. Eternal inflation extrapolates from known physics into this no-man's land, assuming the rules hold where we have no right to expect they will. It's like predicting the weather on a distant planet using only the laws of aerodynamics, ignoring the possibility of alien atmospheres with entirely different chemistry. The stakes couldn't be higher. If quantum gravity alters the behavior of space-time at these energies, perhaps by preventing the infinite stretching inflation, requires the entire multiverse edifice could vanish like a mirage. Some string theorists argue that tiny, curled-up dimensions might stabilize inflation, while loop quantum gravity proposes that space-time is woven from discrete threads, preventing the singularities inflation relies on. Others, like proponents of causal dynamical triangulation, suggest space-time might fundamentally change its nature at high energies, like ice melting into water. Without experimental data, these ideas remain beautiful speculation. This isn't just academic navel-gazing. The Large Hadron Collider probes energies 1 quadrillion times too low to test quantum gravity directly, and cosmic inflation's fingerprints in the microwave background can't reveal what triggered it. Future telescopes might spot primordial gravitational waves, ripples from inflation's first moments, but even these would only be indirect clues, the brutal truth. We're trying to reconstruct a fire from the ashes, with no guarantee the ashes follow the rules we know. Yet the quest for quantum gravity isn't just about saving eternal inflation. It's about confronting the limits of human knowledge. Every great theory in physics has emerged from reconciling contradictions, from Newton's marriage of celestial and terrestrial mechanics to Einstein's fusion of space and time. The quantum gravity gap isn't a flaw, it's an invitation, a cosmic breadcrumb trail leading to a deeper layer of reality. Whether eternal inflation survives this journey isn't just a question about the multiverse. It's a test of whether the universe, in all its strangeness, is even more profound than we've dared to dream. Science has always prized simplicity, the elegant idea that the best explanation is often the one with the fewest assumptions. This principle, known as Occam's razor, has guided thinkers from medieval monks to modern physicists. But when it comes to the multiverse, the razor's edge grows dull. Suddenly, we're asked to accept not just one universe, but an infinite sprawl of them, each with its own laws, histories, and possibly even versions of ourselves. On the surface, it feels like intellectual excess, a cosmic Rube Goldberg machine where a single universe would suffice. Yet dig deeper, and the simplicity argument isn't as clear-cut as it seems. Take the history of astronomy as a cautionary tale. For centuries, the Ptolemaic model of the universe, with Earth at the center and planets moving in perfect circles, was considered the simplest explanation for celestial motion. But as observations grew more precise, astronomers had to add epicycles, tiny loops within orbits, to make the math fit. The system became absurdly convoluted until Copernicus swept it aside with a radical idea. What if the Sun, not Earth, was the center? At first, heliocentrism seemed more complex, even heretical. Yet it turned out to be the truer framework, revealing a solar system far simpler than the tangled epicycles could ever describe. The lesson: what appears simple isn't always what's real. Now apply that to cosmology. A single, finely tuned universe might seem like the parsimonious choice until you realize the staggering improbability of its constants aligning just right for life. Suddenly, invoking a multiverse isn't adding unnecessary complexity. It's offering a natural mechanism for why our universe looks so improbably tailored. Think of it like finding a single, perfectly sanded wooden plank on a beach. You could assume a craftsman carefully placed it there, or you could posit a lumber mill upstream, producing countless planks with random shapes, and the waves just happened to wash this one ashore. Both explanations involve assumptions, but one leans on intentional fine-tuning, the other on statistical inevitability. The debate gets thornier when we consider what simplicity even means in modern physics. Is a theory simple because it requires fewer entities, or because its underlying math is elegant? String theory, for instance, posits extra dimensions and countless universes, yet its equations are strikingly symmetrical, even beautiful. To some physicists, that elegance is a kind of simplicity, a unification of forces that our messy single universe can't provide. Others retort that beauty is a terrible gauge for truth, pointing to the ugly but accurate standard model of particle physics, which resembles a Frankenstein's monster of ad hoc rules. Ultimately, the Occam's razor dilemma exposes a deeper tension in cosmology. How do we judge theories when data is scarce? Without direct observations of other universes, we're left weighing philosophical preferences as much as facts. Some scientists argue that until the multiverse makes testable predictions, it's not science at all, just metaphysics in a lab coat. Others counter that rejecting the multiverse for its complexity is like refusing to believe in germs because they're invisible. After all, the history of science is littered with ideas once deemed extravagant: black holes, dark matter, even the Big Bang itself, that later became bedrock truths. What's clear is that simplicity alone can't be our compass in the uncharted territories of cosmology. The universe owes us nothing, not clarity, not elegance, not even intuitive sense. Our job isn't to demand that reality conform to our aesthetic preferences, but to follow the evidence, no matter how strange the path. And if that path leads to a multiverse, then Occam's razor might need a new blade, one sharp enough to cut through our assumptions about what the cosmos should be and reveal what it truly is. Science thrives on testable predictions, claims that can, in principle, be proven wrong. But eternal inflation dances dangerously close to the edge of this principle, sparking fierce debates about whether it's groundbreaking cosmology or a modern-day epicycle, endlessly adjusting to evade falsification. The heart of the issue lies in the multiverse's sheer scale. If other bubble universes are forever beyond our cosmic horizon, separated by space expanding faster than light, how could we ever gather evidence of their existence? Critics argue this makes eternal inflation untestable by definition, a theory so flexible it absorbs every objection without risk. It's like claiming there's an invisible dragon in your garage that only breathes heatless fire. No experiment could ever disprove it, but that doesn't make it real. Yet defenders counter that indirect evidence isn't just possible, it's already being hunted. Take the cosmic microwave background's cold spot, a mysterious anomaly some theorists link to a long-ago collision with another bubble universe. While alternative explanations exist like a vast cosmic void, the point is that such observations could, in theory, support eternal inflation if patterns align with predictions. Similarly, anomalies in large-scale galaxy distribution or unexpected features in primordial gravitational waves might one day reveal fingerprints of a multiverse. The key, proponents stress, is that the theory isn't inherently unfalsifiable, it's just that the evidence is extraordinarily hard to reach, like archaeologists sifting for a needle in a planetary haystack. The debate intensifies when we consider what counts as legitimate science. History is littered with ideas once deemed untestable: black holes, continental drift, even the Big Bang, that later yielded to observation. The multiverse might follow the same path, its current lack of direct proof reflecting technological limits, not a flaw in the theory. But there's a crucial difference. Those earlier ideas made concrete predictions about our observable universe, while eternal inflation often shifts the goalposts, asserting that most universes are forever hidden. This leaves skeptics uneasy. If a theory excuses every failed prediction by invoking unseen realms, does it risk becoming a metaphysical belief system disguised as physics? Philosophers of science weigh in with a nuanced middle ground. They distinguish between not yet falsifiable and, in principle, unfalsifiable. Eternal inflation, they argue, might belong to the former, a theory currently beyond our experimental reach but not inherently immune to evidence. Imagine a sealed box labeled Multiverse Detector. Even if we lack the tools to open it today, the mere possibility that it could contain answers keeps the idea within science's bounds. The real danger, they caution, lies in conflating ambition with dogma, treating the multiverse as an article of faith rather than a hypothesis to stress test. What makes this controversy so pivotal is how it forces us to confront the limits of scientific exploration. If the multiverse is real but forever unobservable, does that mean some truths are simply beyond our grasp? Or does it challenge us to redefine what counts as evidence, pushing the boundaries of inference and imagination? The line between visionary and unverifiable has never been thinner, but in that tension lies the thrilling uncertainty of cosmology, where the greatest discoveries often begin as heresies waiting for their moment of proof. If our universe is a simulation, then who or what is running the program? This question plunges us into one of the most dizzying paradoxes in all of cosmology, the infinite regress of simulators. Imagine a video game character realizing they're digital only to discover their world is hosted on a computer inside another simulation, which itself exists within yet another layer of code. Where does the chain end unless there's an ultimate base reality, a bedrock universe untouched by simulation? We're stuck in an endless loop of creators creating creators, like mirrors reflecting mirrors into infinity. Some theorists argue this very absurdity disproves the simulation hypothesis. If every simulated reality requires a simulator, and those simulators must themselves be simulated, the complexity grows untenable. It's like a tower of turtles stacked to the sky. Eventually, you need solid ground. This suggests there must be a top level, an original reality where the first simulators exist unsimulated, their physics unconstrained by any higher code. But here's the twist: that base reality wouldn't resemble ours at all. Free from computational limits, its inhabitants might manipulate time, energy, and dimensions in ways we can't fathom, making their existence as alien to us as we are to characters in a pixelated game. Others propose a stranger solution, that simulations can spawn simulations, creating a fractal multiverse of nested realities. In this view, the regress isn't a flaw but a feature, with each layer inheriting slightly tweaked rules from its parent. Our universe might be 1,000 generations deep, its laws of physics the result of countless iterations of cosmic trial and error, the unsettling implication. We could never identify the real universe because every layer would perceive itself as genuine, just as our simulated descendants would swear their world is physical. This raises an existential question: does it matter if a simulation is indistinguishable from base reality? If pain feels sharp, love feels real, and the stars burn just as bright, then functionally, there's no difference. The philosopher Nick Bostrom famously argued that if civilizations ever gain the power to run ancestor simulations, the statistical likelihood is that we're among the simulated rather than the simulators. But even if true, it doesn't diminish our experience any more than learning air is made of atoms cheapens a breath of fresh air. Yet the simulation hypothesis forces a deeper reckoning with the nature of existence. If reality is code, then the universe isn't just governed by math. It is math, an equation running on hardware we'll never see. Particles, forces, even consciousness might be emergent properties of deeper computational processes, like the glow on a screen emerging from millions of pixels. This doesn't just challenge our place in the cosmos, it redefines what the cosmos is. Whether we're in a simulation or not, the mere possibility stretches our imagination to the breaking point, leaving us to wonder, if reality has layers, how deep does the rabbit hole go? The Boltzmann brane paradox is like a cosmic horror story for physicists, an idea so unsettling that some have spent years searching for ways to escape its implications. If eternal inflation truly spawns an infinite number of universes over infinite time, then by sheer statistics, self-aware entities should arise more often from random quantum fluctuations than from the slow, messy process of biological evolution. Enter the Boltzmann brane, a lone, disembodied consciousness that flickers into existence complete with false memories of a past that never was, only to dissolve back into chaos moments later. The chilling conclusion: you're statistically far more likely to be one of these momentary hallucinations than an actual person in a stable universe. It's a scenario that turns science on its head. If most observers in the multiverse are delusional Boltzmann branes, how could we trust any observation, any experiment, any reality at all? Faced with this existential threat to empirical knowledge, cosmologists have proposed clever tweaks to eternal inflation. One approach suggests that universes capable of spawning Boltzmann branes are inherently unstable, like bubbles prone to popping before they can produce more than a handful of these phantom minds. Another argues that the energy required to sustain a conscious brane, even briefly, is so finely tuned that it becomes astronomically rare, like finding a single, perfectly polished grain of sand in a desert the size of the observable universe. The most radical solution comes from quantum mechanics. Perhaps Boltzmann branes cancel themselves out through destructive interference, vanishing before they can skew the cosmic statistics. Each fix aims to restore our confidence that we're real beings in a real universe, not just fleeting glitches in the void, but skeptics aren't convinced. They argue these solutions feel suspiciously convenient, like rewriting the rules of the game to avoid an unwanted outcome. If we're adjusting the parameters of eternal inflation specifically to dodge Boltzmann branes, does that undermine the theory's credibility? It's a bit like a detective ruling out suspects until only the preferred culprit remains. Critics also point out that some fixes rely on speculative physics, like undiscovered particle interactions or untested quantum gravity effects, leaving the debate mired in what-ifs. The deeper issue is methodological. Should a scientific theory be judged by its ability to avoid philosophical nightmares or solely by its predictive power? The Boltzmann brane dilemma exposes a razor's edge in cosmology, where the line between profound insight and metaphysical quagmire blurs. On one side, there's the raw, unflinching acceptance of what the math implies, even if it leads to solipsism. On the other, a pragmatic insistence that any theory rendering science meaningless must be missing something fundamental. It's a tug of war between two visions of reality, one where the universe is indifferent to our need for coherence, and another where the very act of questioning our sanity becomes evidence against the paradox. After all, a true Boltzmann brane wouldn't have the consistent environment needed to develop logic or physics. It would just be a brief, incoherent blip of awareness. What makes this debate so gripping isn't just the technical nuances, it's the visceral unease it provokes. The Boltzmann brane forces us to confront the limits of science as a tool for understanding existence. Can a theory be true if its consequences undermine the very process of seeking truth? Or is cosmology destined to grapple with these shadows, forever dancing at the edge of what's knowable? For now, the paradox stands as both a cautionary tale and a challenge, a reminder that the multiverse, for all its grandeur, might contain reflections far stranger and far darker than we ever imagined. If every possible version of you exists across infinite universes, the hero, the villain, and every shade in between, does the weight of your choices evaporate into cosmic insignificance? This is the ethical quagmire lurking beneath the multiverse's glittering surface. On one hand, if every decision spawns a new reality where the alternative played out, moral consequences seem to dissolve like sugar in water. Why agonize over right or wrong when somewhere, another you already made the opposite call? Critics warn this thinking risks plunging us into existential apathy, a world where accountability vanishes because every action, no matter how noble or monstrous, plays out somewhere else. Yet there's a counter-argument that flips this logic on its head. Instead of diminishing responsibility, the multiverse might amplify it. Imagine standing at a crossroads where each path fractures into countless futures. Your choices don't just shape one timeline, but echo across a web of realities. In this light, every act becomes a ripple in an infinite pond, not less meaningful, but more. Philosophers like Nick Bostrom suggest that if consciousness is the universe's way of experiencing itself, then each version of you is equally real, making ethical living not just a personal duty but a cosmic imperative. The debate gets thornier when we consider suffering. If every tragedy that could happen does happen somewhere, every war, every injustice, every unlived life, does that make compassion futile? Some ethicists argue it obligates us further. If pain is eternally woven into the fabric of existence, reducing it in this universe becomes a defiant act of meaning-making. Others, like utilitarian philosopher Derek Parfit, propose that multiverses force us to rethink morality altogether. If identity splinters across worlds, perhaps traditional notions of blame and praise are illusions, and ethics should focus on maximizing well-being across all possible realities, not just our own. Science fiction offers a playground for these ideas. In Everything Everywhere All at Once, the protagonist's multiversal awareness doesn't paralyze her, it fuels empathy, showing how even small kindnesses resonate across dimensions. Contrast this with Rick and Morty's cynical take, where infinite realities become an excuse for nihilism. Both stories expose the same truth: the multiverse doesn't dictate how we respond to it. It's a mirror reflecting back our deepest fears and hopes about free will. Ultimately, the multiverse's ethical implications hinge on a question older than physics. What does it mean to live a good life in an incomprehensibly vast reality? Whether you see infinite versions of yourself as liberating or terrifying, one truth remains: the choices you make here, now, in this universe, are the only ones you'll ever experience firsthand. And that, perhaps, is where real responsibility lies, not in the infinities beyond, but in the singular, precious present we're given to shape. The hunt for evidence of eternal inflation is entering its most exciting chapter yet, a golden age where next-generation tools could finally bring the multiverse from philosophical speculation into the realm of testable science. Picture telescopes so sensitive they can detect the faintest whispers of gravitational waves from the dawn of time, or quantum computers simulating conditions so extreme they recreate the birth pangs of infant universes in the lab. Projects like the European Space Agency's upcoming LISA mission, a space-based gravitational wave observatory, will scan for ripples in space-time that could carry echoes of primordial bubble collisions. Meanwhile, tabletop experiments harnessing quantum entanglement might uncover subtle anomalies hinting at interactions with parallel realities. We're no longer just dreaming of the multiverse, we're building the instruments to chase it down. But what if the search comes up empty? The stakes couldn't be higher. A confirmed detection of other universes would rank among the greatest scientific revolutions in history, upending our understanding of reality as dramatically as Copernicus displacing Earth from the cosmos's center. Overnight, cosmology would expand from studying a single universe to mapping an infinite fractal of realities, each with its own physics, its own history, its own version of existence. The implications would ripple beyond science, forcing philosophers to grapple with a cosmos where every possible outcome is realized somewhere, and theologians to reconsider traditional notions of creation and design. Even language would struggle to keep up. How do we define everything when reality has no edges? Conversely, if decades of searching yield no trace of eternal inflation, the backlash could be seismic. Without empirical support, the theory risks fading into obscurity like the ether or phlogiston, elegant ideas undone by nature's refusal to cooperate. Some scientists warn this could fracture cosmology, with researchers retreating into safer, more conventional models. Others see a silver lining. Null results often drive innovation, pushing physicists to devise bolder theories or refine existing ones. After all, Einstein didn't overthrow Newton because the old equations failed. He sought deeper harmonies hidden beneath their success. The most intriguing possibility lies between these extremes. What if we uncover hints of the multiverse too subtle to confirm outright? Imagine detecting statistical anomalies in the cosmic microwave background that could be bubble collisions or just cosmic noise. Or finding quantum behaviors that might suggest higher dimensions or merely reflect unknown aspects of subatomic physics. Such ambiguous findings could leave science in a tantalizing limbo, fueling debates for generations. History shows this isn't uncommon. Dark matter was proposed in the 1930s based on indirect clues, and we're still unraveling its mysteries today. The multiverse might follow a similar path, its existence hovering just beyond certainty, teasing us with glimpses but never the full picture. Beyond the telescopes and particle detectors, this quest is reshaping how science confronts the unknowable. Eternal inflation forces us to ask, can a theory be valid if its key predictions lie forever outside our observational reach? Some argue that math alone can guide us, pointing to black holes and the Higgs boson entities once deemed untestable, now confirmed. Others insist science must remain anchored in empirical evidence, lest it drift into pure speculation. The tension between these views isn't just academic, it's a battle for the soul of discovery, determining how far we'll let imagination carry us when reality's edges blur. One thing's certain, whether eternal inflation is confirmed, refuted, or left in tantalizing ambiguity, the search itself is expanding humanity's vision of the possible. Each experiment, each observation, is a message in a bottle tossed into the cosmic ocean, a dare to the universe to reveal its deepest secrets. And in that daring, we're already winners, because the act of reaching beyond the known has always been science's truest triumph. The multiverse may be the ultimate frontier, but the journey to find it, no matter where it leads, is rewriting what it means to explore. Before we dive headfirst into the multiverse, it's worth asking, are we skipping over simpler solutions closer to home? Eternal inflation paints a breathtaking picture of infinite universes, but some physicists argue we might be missing the forest for the fractal trees. Take modified gravity, for example. For decades, we've assumed dark matter must exist to explain why galaxies rotate faster than visible matter suggests. But what if gravity itself behaves differently on cosmic scales? Theories like modified Newtonian dynamics tweak the equations of gravity just enough to match observations without invoking invisible particles or parallel worlds. It's like realizing your car's strange rattling isn't a hidden gremlin but just a loose bolt under the hood. Then there's loop quantum gravity, a rival to string theory that reimagines space-time as a fabric woven from tiny, indivisible loops. Unlike eternal inflation's runaway expansion, this framework proposes that the Big Bang wasn't a singular beginning but a big bounce, a rebound from a previous universe's collapse. No infinite branching, no bubble universes, just a cosmic heartbeat, expanding and contracting in cycles. The appeal, it sidesteps the need for a multiverse entirely while still explaining the universe's uniformity. Imagine a balloon deflating only to be blown up again, each breath smoothing out wrinkles from the last. Quantum mechanics offers its own alternatives. Pilot wave theory, once dismissed as a fringe idea, has seen a resurgence by suggesting particles aren't probabilistic clouds but follow precise, hidden trajectories. If true, it could eliminate the need for parallel worlds to explain quantum weirdness, no Schrödinger's cat splitting reality with every meow. Even the vacuum energy problem, which eternal inflation uses to justify infinite bubbles, might have mundane solutions. Some researchers propose that dark energy, the force accelerating the universe's expansion, isn't constant but decays over time, easing the fine-tuning crisis without invoking a statistical multiverse. The pushback against eternal inflation isn't just about rival theories, it's about scientific philosophy. When faced with cosmic mysteries, should we multiply entities endlessly or search for deeper laws that unify what we see? It's the difference between a detective inventing an infinite number of suspects versus revisiting the crime scene for overlooked clues. Critics argue that invoking a multiverse to explain fine-tuning is like using a sledgehammer to crack a walnut, effective but hardly elegant. Yet the allure of eternal inflation persists precisely because it's so expansive. When other theories patch one hole, it often creates another. Modified gravity struggles with galaxy cluster dynamics. Loop quantum gravity lacks experimental proof, and decaying dark energy remains speculative. The multiverse, for all its extravagance, offers a unifying framework that ties up loose ends from quantum fluctuations to cosmological constants. It's not necessarily the simplest explanation, but in a cosmos this bizarre, should simplicity always win? The real test lies in falsifiability. Modified gravity makes specific predictions about galaxy rotation. Loop quantum gravity leaves signatures in primordial gravitational waves. Eternal inflation, by contrast, risks being the theory that explains everything and nothing simultaneously, adaptable enough to absorb contradictions, but so vast it defies direct testing. That tension forces a humbling question. Are we chasing the truth or just the most captivating story? The answer might not lie in choosing sides, but in letting the universe guide us wherever it leads. Our brains are extraordinary pattern recognition machines, fine-tuned over millions of years to navigate forests, track prey, and interpret social cues, not to fathom the infinite. When faced with concepts like eternal inflation or bubble universes, we hit a cognitive wall. Try visualizing a four-dimensional object or truly internalizing the scale of a Googleplex. It's like asking a goldfish to comprehend the internet. The multiverse doesn't just challenge our knowledge, it exposes the limits of the very hardware we use to understand reality. Consider how we process infinity. Evolution equipped us to think in terms of beginnings and ends, seasons, lifespans, cause and effect, but an endless froth of universes, each spawning more in an unbroken chain. Our minds default to metaphors: bubbles in a pot, branches on a tree, but these are crutches, reducing cosmic vastness to familiar scraps. Even mathematicians struggle. Infinity isn't a number you can count toward, but a conceptual abyss where logic twists back on itself. If the multiverse is real, it might be like an ant trying to map New York City using only pheromone trails, an analog for something far beyond its sensory world. This raises a haunting question: are some truths fundamentally ungraspable? Philosopher Colin Maginn argues that certain aspects of reality might lie permanently outside human comprehension, not because they're complex, but because our brains lack the necessary cognitive plugins. Think of it like a computer trying to run software it wasn't designed for. No amount of updates will help. In this view, multiverse theories aren't just difficult, they're like trying to smell a color or hear a photon. The math might check out, but the visceral understanding eludes us forever. Yet history offers glimmers of hope. Concepts once deemed inconceivable, Earth orbiting the Sun, quantum superposition, eventually became textbook fodder. Our ancestors would have balked at the idea of invisible waves carrying music through the air, yet here we are, streaming podcasts on devices thinner than a pencil. The difference, those ideas, however strange, could be tested. The multiverse's real challenge isn't its grandeur, but its potential untestability. If we can't interact with other universes, even indirectly, does that relegate them to the realm of metaphysics? Some scientists retort that black holes and quarks were once equally speculative. Absence of evidence isn't evidence of absence. The tension here isn't just academic, it's existential. If our cognition caps out at a certain scale, does that mean reality's deepest layers will forever be a locked room, or is the struggle itself the point? After all, the universe didn't evolve to be understood, but understanding evolved to navigate the universe. Pushing against these limits, however futile it seems, might be the most human thing we can do. Whether we're glimpsing the edge of knowledge or just the edge of our own imagination, the act of reaching matters as much as what we find. And that's a mystery no theory, no matter how infinite, can fully resolve. From quantum bubbles to simulated realities, the 32 models of eternal inflation don't just stretch our imagination, they shatter the very framework of how we perceive existence. Each theory, whether rooted in mathematics or metaphysics, forces us to confront an unsettling truth. The universe operates on scales and principles that defy human intuition. The sheer audacity of these ideas, parallel worlds, holographic projections, cosmic rebirth reveals how small our corner of reality might truly be. Yet for all their grandeur, these models share a common thread. They're born from humanity's unrelenting drive to make sense of the incomprehensible. Consider the irony: the more we learn, the stranger the cosmos becomes. Centuries ago, we believed Earth was the center of creation. Then came the Copernican revolution, revealing we orbited the Sun, a minor star in a vast galaxy. Now, eternal inflation suggests even our galaxy is a speck in an infinite froth of universes, each with its own laws, its own history, its own version of time. It's a humbling progression, one that chips away at our cosmic ego with each new discovery. But humility isn't the same as defeat. Every radical idea, from quantum fluctuations birthing universes to black holes incubating new realities, is a testament to our refusal to accept superficial answers. The absence of definitive evidence doesn't diminish the value of these theories. It underscores the boldness of the questions we're willing to ask. Science isn't just about answers, it's about the pursuit of deeper truths, even when they lurk in the shadows of the unobservable. Think of the atomists of ancient Greece, who postulated invisible particles millennia before microscopes could confirm them. Or Einstein's gravitational waves, theorized in 1916, but not detected until a century later. The multiverse might follow the same path, a seemingly outlandish idea awaiting its moment of validation or revolution. What's truly remarkable isn't whether these models are proven right or wrong, but how they reshape our relationship with the unknown. The multiverse isn't just a scientific hypothesis, it's a mirror reflecting our capacity for wonder. It challenges us to live with uncertainty, to find comfort in the unresolved, and to keep probing the darkness beyond the edges of our understanding. After all, every great leap in human knowledge began as a heresy, a whisper against the dogma of the day. So where does this leave us? Not with tidy conclusions, but with something far more valuable, a universe or multiverse teeming with mysteries yet to be unraveled. The greatest gift of these theories isn't their answers, but the questions they inspire. What lies beyond the cosmic horizon? Are we alone, or just one thread in an infinite tapestry? The search itself is the adventure, and the next revelation might be waiting where we least expect it. Until then, keep looking up, keep questioning, and never stop marveling at the fact that we tiny, fleeting, and impossibly curious get